Just enough physics. Okay, chapter 3. I'm still in this vector stuff, okay? And in the last example, we did a projectile motion problem where it started from the ground and ended on the ground. So now we're going to do the projectile motion problem to end all projectile motion problems. And I don't think there's anything necessarily awesome about projectile motion, but it comes up all the time, so I think it's a useful case to play around with. Okay, so here is the situation that I have. I'm not going to use numbers, and you'll see why. Here I have a ball launched with some initial velocity v1, that's the magnitude of the velocity, at some angle theta, and this is starting on some cliff of height h, and it's going to go down over here. And so this is at x equals 0, y equals h, and it ends up down there, and I want to know where it lands. It's going to be great. Okay, so the first thing is if, and this is all what we did before, so it's not new. The first thing is to say my initial x velocity, v1x, is v1 cosine theta. Because remember, if I have this launched at an angle, then this is a right triangle. The horizontals, the adjacent sides would give me the x velocity, which I could find with the cosine theta, and the vertical side would be from the sine theta. So I have v1y is v1 sine theta. Okay, and these are the initial velocities, because actually as this thing moves along, then it has a downward acceleration of g, and only in the y direction, so the x velocity stays constant. So if you remember, I broke this into an x motion problem and a y motion problem. In the x direction, I have x, let's call this x2. x2 equals x1 plus v1 cosine theta delta t plus 1/2 ax delta t squared, but that's 0. So that's really the only equation that I want. So I know that x1 is 0, x2 I don't know. Let's say I do know v1 and I do know theta. I'm not going to say what they are right now. Okay, we're just going to solve it without those values. Okay, now in the y motion, which I kind of messed up a little bit, I have the following equation: y2 equals y1 plus v1 sine theta delta t minus 1/2 g delta t squared. And that's what I did before. Now remember, this is a y component equation. So that g is not the vector g, that is the component of g in the y direction. That's why it's negative. And so that g is 9.8, not negative 9.8. G, the magnitude, is 9.8 meters per second squared. Okay, now what do I know? I know y1 is h, y2 is 0 because it hits the ground, and I know v1, and I know all that. Okay, so let's just write this equation. So it's going to be 0 equals h plus v1 sine theta delta t minus 1/2 g delta t squared. Okay, now I know everything in this equation, supposedly. I know h and v1 and theta and g. I don't know t. Okay, and I can just call this t now, because if I say t equals t1 equals 0, then the final t is this t. So how do you solve this equation even if I had numbers? Well, the answer is I could call this term, or this one right here, a is negative g over 2. I could say this term, not the t, b equals v1 sine theta, c equals h. And maybe you see that I have a t squared plus bt plus c equals 0, and you solve that with the quadratic equation. Okay, so the quadratic equation says once I know these values, which I can calculate, okay, and I'm not going to write it out all the way because that's the beauty of how we're going to solve this. I get t equals negative b plus or minus the square root of b squared minus 4ac over 2a. Now, I get two answers here. I'll go ahead and tell you that one of them is going to be negative, and I don't want the negative one, because what I'm solving for is that the time that this gets back to 0. Well, there's two. There's one right here, and there's one if I trace this back to where it started in back in time, because the equations don't know it's not real, right? So it finds these two roots. That one's negative, and I don't want that one. So I'm going to use whatever I need to do in here to find this positive. Remember, a is negative, so I'm probably going to take the well, it doesn't really matter. Yeah, I'm going to take the negative. Okay, so how do we do this? Well, we want to find out where it goes. I know everything here, so I can plug it in this equation. I know everything here. After I find that, I know everything here, so I can plug in that equation. So step 1 is calculate this. This is step 1. Step 2. Step 3. And that's it. Okay. I know you're thinking, boy, that's no fun. Okay, I agree. But here's the thing. I now know any values, starting values, I can find out where it goes. Anything. I could even let h be 0, and I should get back to where I was. So what I want to do is put this in a Python calculation, and then I can recalculate things whenever I want. I can recalculate the range as a function of theta. So I want to be able to make this, right? Let's call this x as a function of theta. What does it look like? And where is the maximum x at? Isn't that pretty cool? I could also change it with change the velocity and stuff too, which I'm not going to do. I'm just going to change it to theta. And I want to find the range, the maximum range here. Okay, so that means I'm going to use Python. So I'm going to switch over to the computer, and I'll see you there. Bye. Okay, so here is my blank thing. I already know what I'm going to do, but let me just go ahead and pick some values. So I'm going to say I need to start with some values. So V1 equals, I'm picking something 2.8. Theta, let's launch this at 22 degrees. So 22 times pi divided by 180. I need to have the angle in radians. That's just what Python expects. H is going to be 1.4 meters. G equals, now I've already broken this into two one-dimensional problems. So I'm going to use G equals 9.8. What other values do I need? That is it, I believe. Yes. Okay. So let's do this first just one time. The first thing I said was to calculate A, B, and C. So A is going to be equal to negative G divided by 2. I don't need to print that out. I don't know what it is. Don't really care. B is going to be V1 times the sine of theta. Don't need to print it out. C equals H. Now I can say, let's just do this twice. TP is going to be equal to negative B plus, that's the T, the P stands for plus the square root, this is square root in Python, surprise, B squared, squared is star star. I know a lot of people think, oh, it's squared, it's like that. No, it's not. I don't know why, it just is. Minus 4 times A times C, and that is all divided by 2 times A. So let's do the same thing. I can copy this, paste it, and this is T minus, and that's going to put the minus right there. And then let's just print these. Print TP equals TP. I'm not going to put the units in there. And then put T minus equals T minus. Now I'm going to save it, and I'm going to run it. Save, run. Okay, so here you see I told you I was right. The positive value is not going to work. It's going to give me a negative time, so I'm going to go with the minus time. And that's going to be true for all of them, so I'm just going to assume that's true. And also, let's just double check here. It's 0.65 seconds. It's launched off of a thing that's about 1.5 meters high, so it's not super high. It shouldn't take super long in the air. That everything seems legit. Okay, so I don't need to print these things out again. I'm just going to delete them, or I'm going to comment them out. So if I comment them out, then they're there, and if I want to turn them back on, I can. Okay, so that was step 1. Step and that was step 1 and 2. Now step 3, I can say x2 equals x. Oh, and let's put in here some more stuff. Watch this. x1 equals 0. Y1 equals. No, I don't need to do that. I've already taken that into account. Let's see. Wait, where did I put that? Yeah. Okay, that's it. So x2 equals x1 plus v1 times cosine theta times t, tm. Let's just call that t. Print x2. Okay, so that's how far it went. Yay. Not super cool though. Okay, now what do we want to do? I want to like take it and launch it at an angle of 0 degrees, and then maybe 1 degree, 2 degree, 3 degree, 4, and I want to all the way up to 90 degrees, and I want to see all those results. So that suggests to me, hey, let's make a graph. Okay, so I'm going to go up here and say t graph equals graph, and it's of object graph with the x title theta. And this will be, let's plot it in degrees. I'm going to plot it in degrees. And the y title is equal to range in meters. Okay, good. And then I'm going to say f1 equals g curve. And then the color is blue. I think I went over, if you don't remember how to make graphs and stuff, I went over it in the kinematics section in chapter 2. Where's it, chapter 1? Chapter 1. Chapter 1, I did that. Okay. So now I need to come down here and say, I already said this is theta. Let's put theta is equal to 0. Now I need d theta. D theta is how much I'm going to increase theta each time. So I can say d theta is 1 degree. So it's going to be pi divided by 180. Okay, you can just pick a number too, it doesn't matter. I always think in degrees, I don't know why. Let's get rid of this. Okay, so now what we're going to do is calculate this stuff every single time. Okay, so we could make this into a function, but I don't want to get there yet. So I'm just going to say while theta is less than 90 degrees, which is pi over 2. I'll put this in parentheses just to make sure. Do the following. Now I'm just going to do all of this stuff right here. Okay, so I need to, this stuff is not going to change. That's all the same. This stuff I do need to calculate, so I'm going to copy that, paste it right there, tab indent so it's in the loop, not the x, that's not that one didn't change. And then I need to calculate this, the t minus, so I'm going to copy that, and then I need to calculate this. Now I have it. Okay, now I need to plot that data point. So I'm going to say f1.plot. And what did I say is the x-coordinate? It's going to be theta in degrees. So it's going to be theta times 180 divided by pi. I'm converting it back to degrees. And then my x value, so x2. I think, I almost messed up. Then I need to say theta equals theta plus d theta. So at the end of the loop, I need to add a little bit to theta to do it again. Otherwise, this will just go on forever and I'll look silly. And I'll never end this video, and that's not good. Okay, so let's run it. And something happened. X title is not a thing because I spelled it wrong. Boom. There you go. So this is not the trajectory. Okay? This is the range as a function of theta. So let's just look. Where is the maximum range? Well, it's right here. The maximum range is at an angle of 25.6 degrees, and it goes 1.7 meters. Now you may think, oh, I thought the max range was at 45 degrees. Well, that's true if it starts from the ground. So let's go over here and change this to the ground. And let's rerun it. Okay, now the range goes higher and higher and higher until it gets up to here at, what do you know, 45 degrees. And then it also, if you shoot it straight up, it comes back down to 0. It never goes anywhere. And if you don't shoot it at all, it goes right there too. So, but now I can put this at whatever I want. I can put this at 0.5 meters and run it. Where's the maximum range? There you go. Isn't that cool? Now, you could say, well, what about if I change the initial velocity? What's the maximum range then? Well, I'll tell you. As you increase the velocity, it's just going to go farther. Okay, so that's not nearly as fun. But this is fun. You can also find this by writing out this stuff as a function and taking the derivative, but I kind of like this way, and I'm kind of happy with it. Okay, so just enough physics. We're still in chapter 3. I'm going to do some forces next. This is projectile motion. If you like this stuff, subscribe, like, Patreon. Peace out. Talk to you guys later.